So thank you. And I will speak about the general purpose Lua interpreter from Modelica, as already mentioned. So what is the plan for the next 15 minutes? First, I want to answer a few questions, rather general. So why would you need a scripting language in Modelica anyways? Why that language should be Lua? Then I will go into our implementation. How does it work? How would you use it to build a model with that? Then a bit more into detail, how you synchronize that model with Modelica. And then I will already go into two examples and then, of course, conclude. So first, why would you need something like a scripting language in Modelica? And I think we can all agree there's stuff that is easy and good, that works very well, generally everything equation-based. So everything mechanical, electrical, thermal, low-level control logic works quite well. So a PID controller somewhere, so also no problem at all. And there are many, many other examples, as shown by all the talks here, that work well. Then there's stuff that works, but well, not so well in our opinion. That is mainly everything connected to a high-level control logic. So if you want to have something that switches depending on complex states and then decides what to do, or just a sequential list of actions that vary quite a lot, that's all possible, but somewhat tedious and strange to do, let's say. And depending on, in many applications, being it's simulating a rover that goes to Mars or simulating an assembly line with robots, both of them need both things. So you have that physics equation-based part and that logic part that governs the actions of the system. And both are important and both need to be modeled if you want to evaluate the system's performance. One good solution for that is to build your physical model in Modelica, then export it via the FMI standard, and then import it into some other tool like MATLAB or whatever, and then build your logic around that and then test it in that way. In our case, we couldn't do that. We needed to have everything within our one model and one executable. And a good solution we found was to implement a scripting language in Modelica, since we knew that a scripting language could solve our problems with the high-level control logic. So why would we then use Lua and not something else? I will heavily quote Lua's own webpage here that describes itself as a powerful, efficient, lightweight, and embeddable scripting language that supports many, many different aspects of programming. The two keywords here are lightweight. So if you compare it, for example, with Python, Lua doesn't have the hassle of caring about all the packages and so on. So getting it to work is quite simple. That was one key factor. And the other one, even more important, is that it is embeddable, so that we could embed it in our library at all. The next part is that Lua is implemented as a library, which is true, and that is written in clean C, the word is also true, and that just made it very easy for us to integrate it with the C interface of Modelica. Then also quite important, Lua is free, and it comes with the MIT license, so integrating it with the library and then using that library in some applications and sharing that library is no problem. Then to the usability of Lua, if we look at Stack Overflow, how many questions there are as like a metric for how easy it is to get answers, then it has roughly 20,000 questions for Lua. To compare, Modelica has roughly 1,000, C 350,000, and Python 1.7 million. So Python completely out of the competition, but with the 20,000 questions and the ones that are there, it's easy to get started with it. And there are also very good tutorials on how to get started with Lua. Then it's actively used, and that is the reason why there are this many questions there in both professional and game development. Some professional examples are Adobe Lightroom uses it quite a lot. The FreeBSD's bootloader is in there, and many, many other examples. And on the gaming world, the CryEngine uses it, Minecraft and Factorio both use it. So there are many applications of Lua, and that leads to many libraries are being available that align quite good with what we need them to be for using them in controlling a robot. So state machines are there, 3D vector math is there, and with that you can already build a lot. Then how does our implementation work? So on the one side, you have your Modelica model. On the other side, you have your script, and you need to put the interpreter somewhere in between. We did that by encapsulating the interpreter in an external object together with the data core, as we called it, where both sides can read and write to, since both of these things, so the Modelica main thread and the Lua interpreter run in a different thread, so it needed to be thread safe. We provide interfaces to that. On the Modelica side, it's just simple get and set blocks for all data types, so real, integer, and Boolean. String is not shown here, but it's also there. And on the Lua side, we added a special library that you can use so that you can get and set values. With that design, you also have the benefit of using multiple interpreters in one model so that you can have different robots doing different stuff, or one for your robots and one for your environment or whatever. So how would you use that to build a model? On the left side, you see our library. It's quite small, and its key element is the Lua block, which you drag in your model. It's defined as an inner block so that it communicates downwards for all the get and set blocks. The key element in here is the definition of the script. You can either do that by pointing towards a file, or you could directly put the string in here that is your script, if that is desirable to you. The next aspect is related to synchronization and timing. I will explain that in more detail on the next slide. And the next option is when you want to start your script. Usually that starts when your model begins, but there might be cases where that is not needed and you need to start at a specific time or based on some event or so. Then you would use the set blocks, in this case a real block. It is only defined by its key, so the name where this value then is found in the data core, as well as the size of this value. Everything is defined as an array so that we could reduce the number of blocks. Same goes for the get blocks, in this case for an integer. Get blocks also have the additional option to set and specify the start value in the data core. For the set blocks, that is just defined by the value, the start value of the input. After that, you then need to connect your extremely complicated and sophisticated Modelica model and run it. And for everybody who's already looked into the code, it's a quite simple model that just counts the number of times the input value exceeds the threshold and then increments the count and resets it. And that would have been, I must admit, a lot simpler to do it directly in Modelica, but it was a nice example. So back to the synchronization topic, we have that sample time parameter, which just specifies the rate of an event that triggers an update of the data core back and forth between Modelica and the data core. And to then synchronize your script between Modelica and Lua, you have two options. The one doing it manually, we provide two functions, modelica.wait and modelica.waitUntil. Wait just blocks until the specified time has passed, and wait until blocks until specified simulation time is reached. So if you put 10 in there, this block will this function will block until 10 seconds is reached. The resolution of these wait functions is, of course, always governed by the sample time parameter. The second option is use a loop synchronization, somewhat inspired by how you write Arduino code. So you have that while loop, and everything above the while loop is your setup, your initialization, and everything within the while loop is executed once per sample time. And then you have these two synchronization options, Modelica wait and Lua wait, that specify if one should wait for the other. And if both are set to true, it is made sure that even if one of the two runs very slow, they both exit this while loop, start this while loop at the same time. And with that, you can do most things that you would desire. One thing we're currently working on is implementing callbacks so that you can trigger the execution of functions in Lua based on events in Modelica. But that will come in a version 2.0. So I will already start with examples. The first is the DLR robots library, and I will use that to show one more feature of the Lua library, and that is the logger. You can see these lines here as well. If you look into the pause program function, you see some string outputs here, and that just allows you to create an additional window that displays the state of your script. And if you combine that with visualization, for example, from the Visualization 2 library, you have a very powerful combination of understanding what is happening in your script and in your model. You could also parse those directly to the Modelica, the log file that is created, but in many cases that isn't as handy for debugging as this configuration. The next example is from actually the next talk. It's from the object manipulation library. And that is just an example where two robots are controlled by individual Lua interpreters, and both robots are doing their own thing. And what they are doing will be explained in the next talk. The next example, I will need to explain a bit more. That comes from the MMX and MMX rover mission. So MMX stands for Martian Moons Exploration. It's a JAXA mission to the Martian moons Phobos and Deimos. It will launch in 2024 and arrive there in 2026. And part of that mission is a small rover, roughly half a meter by half a meter, that is developed by CNES and DLR. And its task to de-risk the spacecraft's landing that brings a sample back to Earth just by being the first one down there and giving information on the surface. And as an engineer, the most interesting part of that is actually that it's the first wheeled locomotion system in a milli-G environment. Milli-G means that the gravity is roughly 1/2000th of that of Earth on Phobos. It varies quite a lot depending where you land. But that leads to that all robotic actions of the rover have to be tested quite thoroughly, and you have no way of doing that on Earth as gravity isolation is not there yet. So we needed to test all that in simulation before, and we needed to do that before we had any hardware or any of the real software at hand. So we did build the model of the rover in Modelica, and then used the Lua library and built a library that abstracted away all the pesky details of running that robot. So for example, if you wanted to open the navcam shutter, there's just a function without any arguments that you could call and that opened the navcam shutter. And this function then took care of all the details and the states that were required in Modelica to make this work. Also, we could provide functions like legs at target, which checked if the legs are already at the given target. And that was just extremely simple to do in Lua. And with that, you could already write pretty simple functions or programs that let the rover drive a couple of centimeters and then lower its height down to a given target, and then wait for the robot to reach that target. These simple programs were quite useful to test a lot of stuff, but where it really got useful is once we were looking at uprighting. Uprighting is the phase where the rover came to rest on the surface of Phobos and now needs to reorient itself back to its belly and then stand up. This sequence needs to function from all 6 sides of the robot. And in general, that can be described as a state machine. And what you're seeing here is the state machine governing just the actions of the rover. There's one above that then governs what happens depending on what situation. But that was no problem at all to implement. And every state had an on-enter, run, and on-exit function. And these all were quite simple. With that, we could then run many thousands of simulations, since all those simulations were just a single executable pointing to one script. And those could run on their own and test how good this algorithm is. And if we wanted to change something in the algorithm, we didn't have to recompile our model. We just had to change one single file and change the duration of how long something waited between 2 actions or something. And that gave us the chance to very quickly find an algorithm that very reliable uprights the rover to its belly. One thing you can see, I hope you can see my mouse, you see that lock here. That is more or less the same lock as was in the additional window before. In that case, it was just a bit more handy to have it here, so that we can have one single video at the end of every test where we can identify, oh, okay, it failed in that case or something. And with that, I want to already conclude. So to cite Lua again, a powerful and efficient, lightweight, embeddable scripting language is now available in Lua and Modelica. And we provide a slim and comprehensive interface between Modelica and Lua that allows you to integrate it with existing models. It gives you quite flexible synchronization options and multiple interpreter instances. And as an outlook, we still have 2 to-dos on our list to implement those callback functions and make sure that it works on all platforms. And once that is done, we want to release this as open source in 2022. And with that, I'm done and open for questions.